Hello, I'm Yuxing from National Taiwan University. In this presentation, I will introduce our work published in ICCV 2023. Our work primarily aims to combine weakly supervised learning into the problem of continual learning for instance segmentation to reduce the time and effort for annotation, which is abbreviated as CO for WSIS. That is, after the base task, only weak labels are provided for each new task. As far as we know, this is the first work to consider this scenario. Because we want to achieve instance segmentation by first learning semantic maps from image labels, we adopt the representation method from Panoptic Deep Lab. This representation simply directs each program pixel in semantic map to an object center using a 2D offset to represent instances. In the following, I will give an overview of our method. Our method uses an encoder followed by a segmenter to learn the three maps as mentioned in the previous slide. First, to generate the semantic maps from current step image labels, we use an aggregator to aggregate the maps outputted from the decoder D into a classification vector to compute the classification loss. This is a common pipeline which can be seen in weakly supervised semantic segmentation. This training strategy allows the model to generate semantic maps by mapping back to the output before aggregation. After getting the semantic segmentation results, we then use a location queue extractor to extract instance queues and generate center and offset maps for the segmenter to achieve instance segmentation. The top part have helped us to achieve instance segmentation for current classes. To also preserve knowledge learned in previous steps, we use the knowledge distillation technique to make our current model mimicking the response of previous model. Since the semantic segmentation result is important for us to achieve better instance segmentation, and learning only from image labels may simply lead to incomplete segmentation results, we first propose two strategies on the multi-label classification module to improve W3S. The first one is random dropouts. Its idea is similar to previous methods that masking out object parts in the image to guide the model focus on different regions. Instead of manipulating the images, we take advantage of the aggregator we used to drop out the contribution of pixels to achieve similar effects without big modifications. Another one is inspired from recent weakly supervised object detection methods, which uses the idea of augmentation consistency. Compared to previous methods usually apply augmentation on input images, we apply on the lower dimension feature level for better efficiency. For phase 2, we propose peak generator PG, which aims to generate an accurate queue or say peak per instance to help us identify useful masks in semantic segmentation to generate center and offset map. This generation process was proposed in a recent WSIS work. Our PG can generate more effective queues compared to previous method by considering the semantic segmentation information. We also propose selective distillation to tackle the background shift problem while learning old center and offset maps. This problem happens due to the old class maps only contain information of previous time steps, and some instances of current classes may be unlabeled. To prevent incorrect learning, we use the semantic segmentation result, which already contains knowledge from old tasks to guide the distillation. That is, distilling only old class regions identified by semantic segmentation. Since we are the first work of CO for WSIS, we adapt previous WSIS methods into continual learning for comparison. We use Pascal SPD, which contains 20 classes, and divide them into multiple tasks, and also a COCO to VOC setting, which first learned the 60 non-VOC classes in COCO, and learn the VOC classes in the second task for comparison. Compared to previous adapted methods, our method almost always achieves the best results. We also compare on the continual learning for W3S part with a recent work Wilson, which shows our method is also possible to improve the CO for W3S. Another interesting setting is that since image labels are cheap compared to fully annotation, we also consider a scenario where both old and current class labels are provided in each task. The result shows that by providing extra old class labels, the model can learn better compared to providing only current class labels. In sum, we conduct the first study of CO for WSIS, and our method can improve CO for W3S and achieve CO for WSIS effectively. Thank you.